Hello guys, welcome to the data structure and algorithm series. In today's video, we will be giving you a high level understanding of what the subject is all about and why it is crucial for your programming and problem solving skills. Data structure and algorithms are the backbone of computer science and are essential for building the efficient and scalable software. So whether you are working with databases, AI or developing application, a strong grasp of these concepts will set you apart. Throughout this series, we will explore various data structure, how they work and how algorithms help us to solve the problems efficiently. Stay tuned with us as we dive deeper into each topic in the future chapters. Let's get started. At first, introduction. Data structure and algorithm form the core of the computer science, providing the foundation for efficient software development. Data structure are ways to organize and store the data, while algorithm define the steps to perform the task like the searching, sorting, and modifying the data. A solid understanding of these concepts helps to optimize the performance and solve the problems effectively. From the real world or real time application like the social media feeds to the complex systems such as databases, these topics are critical. Understanding operations like the insertion, deletion, and traversal is essential for implementing most algorithms. Algorithms are measured by their times and the space complexity, which are analyzed using the asymptotic notations like the big O. This helps to evaluate their efficiency. In this series, we will explore the key structures like the stack, queue, trees, graphs, and dive into essential algorithms like the sorting and searching. Mastering these concepts leads to the better programming skills and lays the groundwork for solving more advanced problems. This series will gradually build your expertise in both theoretical and the practical aspect of this subject. So now, stack and queues. Stack and queues are the fundamental data structure that operate in the specific ways. A stack follow last in first out principle, meaning the last element is inserted at is the first one to be removed. Queues, on the other hand, follow the FIFO rule or the first in first out, where the first element inserted is the first to be removed. Stack is often for recursive operation and expression evaluation, while queues are used in scenarios like the task scheduling and managing resources in the operating system. Operation on stack include the push, pop, pick, while queues have unique have NQ, DQ, and front operations. We will also cover the different type of queues like circular, priority, each with their specific use cases. In this chapter, we will discuss how these operations are implemented, their time complexity, and the real world application. Understanding how to manipulate these structures effectively will enhance your ability to design efficient algorithms. We will also explore how stack and queues can be applied in problems like balancing parentheses and managing the function calls. With in-depth analysis and examples, you will gain a strong grasp of these essential data structures. So now, linked list. Linked lists are a type of linear data structure where each element or node contain the data and a reference or link to the next node in the sequence order. Unlike arrays, linked lists allow for efficient insertion and deletion operation, as element can be added or removed without shifting the other elements. Singly linked lists have nodes with single link to the next node, while doubly linked lists allow the traversal in the both direction with two links, next and the previous. Circular linked lists connect the last node back to the first, forming a loop. We will cover the advantages and limitations of linked lists compared to arrays, focusing on memory management and access time. Linked lists are ideal for dynamic data structure where the size of the data set can change frequently. In this chapter, we will examine how to perform the operations like traversal, searching, insertion, deletion, and we will analyze the time complexity of each operation. Linked lists are used in application in like dynamic memory allocation, implementing the stack and queue, and managing the polynomial expression. By mastering the linked list, you will learn how to handle the flexible and efficient data organization. So now, a tree is a hierarchical data structure consisting of nodes connected by edges, with a root node serving as the starting point. Each node may have multiple child nodes, and the structure represents the relationship such as organizational chart or the file system. Binary trees, where each node has at most two children and are widely used in applications like searching and sorting. Binary search tree are the type of binary tree where the left child node contains the value smaller than the parent node and the right child node contains the larger value, allowing the efficient searching. AVL tree are the self-balancing BST that ensure the optimal performance by maintaining a balance factor for each node. Threaded binary tree introduce the link between the node to make in-order traversal faster without recursion. B tree and B plus tree are used in the database system for efficient storage and retrieval. This chapter will cover the tree operation like the insertion, deletion, searching and balancing, focusing on their algorithms and complexities. We will also discuss the practical application of trees in the real world system, from the search engine to the file management system. So now the graphs. So graphs are a non-linear data structure that consist of nodes or called vertices connected by edges. They are used to model the relationship like the network, social media connection and routes on map. Graphs can be directed or undirected. Weighted graphs assign a weight to the each edge, representing the cost of the traversal. A key operation in the graph theory is traversal, where we visit all the nodes in a specific order. DFS and also BFS are important algorithm. So graphs can be implemented using the adjacency matrices or the adjacency list, each with its own advantages. In this chapter, we will discuss the various algorithms for graph search, including the DFS, BFS, shortest path algorithm like the Dijkstra graph algorithm. So, graph algorithms are critical for applications in networking, pathfinding, and data structure optimization. So, now sorting algorithms are designed to arrange the data in a specific order, typically in ascending or descending sequence. Selection sort, bubble sort, insertion sort are simple but inefficient for large dataset. With time complexity is more. So more efficient algorithms like the quick and merge sort, they use the divide and conquer strategy to sort the data. So heap sort is there. Heap sort use the binary heap structure to sort the element in place. In this chapter, we will compare these sorting techniques in terms of time complexity, stability, and use cases. Hashing is a technique used to map the data to a fixed size arrays using the hash function, allowing for the fast data retrieval. Hashing is especially useful for implementing the efficient search operation. We will also discuss the collision resolution techniques such as chaining and open addressing, which are critical for maintaining the efficiency of hash table. Sorting and hashing play a major role in optimizing the algorithms and improving the performance of data-driven application, making them essential skills for any programmer. So now some miscellaneous topics. So some advanced topics in the data structure and algorithms that are essential for solving the complex problems. So these include the specialized algorithms for dynamic programming, greedy approach, graph-based algorithms such as minimum spanning tree, and the shortest path problem. We will also touch on space-time trade-offs and how to make algorithmic decision based on the available resources. Understanding how to apply multiple data structure and choose the right algorithm for a given problem is key to writing efficient code. Additionally, we will discuss memory management technique, amortized analysis, and the implementation of advanced data structure like the tries, segment trees. These miscellaneous topics will broaden your knowledge of how to approach algorithmic challenges and optimize your solutions for real world scenarios. By the end of this section, you will have a well rounded understanding of not just the foundational data structure and algorithms, but also advanced concept that elevate your problem solving ability. So that's wrap up our overview of data structure and algorithms. I hope this introduction has sparked your curiosity and given you a clear idea of the topics we will be covering in detail. As we progress through the series, we will break down each concept, provide the examples, and guide you through the algorithms step by step. Make sure to like, share, and subscribe for the more videos in this series. If you have any question, feel free to leave them in the comments below. Stay tuned, and I will see you in the next chapter.